And welcome Ryan to the stage.
Hello everyone, I'm Ryan. I studied physics here at Curtin and now I'm working with the Curtin Carbon Group on climate science and green technology. Because our climate is changing. The ice is melting, the seas are rising, the atmosphere is heating up. But why? The answer is greenhouse gases, in particular carbon dioxide, CO2. It is the most significant greenhouse gas and accounts for the most global warming associated with human activity. The concentration of CO2 in the atmosphere has increased more than 50% since before the Industrial Revolution. More than a 50% increase, and it's making the Earth warmer. Light that shines from the sun turns into heat when it hits the Earth. Then CO2 absorbs some of the heat that would otherwise radiate back out into space. There's a lot of CO2 in the atmosphere, and it's a problem. So, how much? And how do we measure it? Well, Earth's atmosphere is mostly nitrogen at 78%, oxygen at 21%, and a pinch of argon at almost 1%. If you're following the maths in your head, that's basically 100%. CO2 is the next highest though, but in comparison, there's not very much at all. It's so not very much that instead of using a percentage, we use parts per million to represent the amount out of a million. And as of right now, there's 430 parts per million of CO2 in the atmosphere. Out of 1 million air molecules, just 430 of them are CO2. That's less than 0.1%. And I know what you're thinking, but wait, the atmosphere of Mars is almost all carbon dioxide. How come it doesn't experience heating like Earth does? Well, it's because Mars's atmosphere isn't very dense. Although it's almost all a greenhouse gas, there's just not enough gas in general to absorb the heat. So Mars is ice cold. On Earth, however, we have a thick blanket of an atmosphere. It's more than 50 times denser than Mars, so the greenhouse effect is much stronger. But how do we know this? How do we measure it? We can't see carbon dioxide. Most gases, including greenhouse gases, are invisible. They're completely colorless. However, we can hear it, and I can show you how it works. Spoiler alert, this involves being able to hear something, and the sound the demonstration makes is too faint to pick up by the microphone, so I'm just going to play what it sounds like out of my phone. It's not a very interesting sound, but we've made the sounds interesting in the John Curtin Gallery. We have displays there and you should definitely check them out. But what's happening here? It's called photoacoustics. Photo meaning light and acoustic meaning sound. And I know what you're thinking, whoa, that's got to be what his whole talk's about. How does that work? Well, this torch emits visible light, like the light that comes from the sun, and beanies are good at keeping in heat, just like greenhouse gases do on Earth. This torch is very powerful and has a dim setting. This dim setting works by turning off and on again super quickly, but instead so fast that we can't even notice. When I cover it with the beanie heats up when it's on and cools down when it's off. Very slightly, but very rapidly. When something heats up, it absorbs thermal energy and the motion of the molecules increases. They vibrate. This vibration causes the molecules around it to vibrate too. These vibrations travel as a wave, and this is what we can hear as sound. The same process is used to measure CO2. We shine a pulsing light at the gas heats up and vibrates and makes a sound. The higher the concentration of CO2, the more the gas heats up, the more it vibrates, and the louder the sound becomes. This technique is called photoacoustic spectroscopy, and it's how we are listening to climate change. And that would make a good place to end. But as we continue to measure the concentration, the number continues to go up. Climate change is still a problem. And I know what you're thinking. You're thinking, Ryan, I care so much about climate change. What can we do about it? Well, I'm so glad you asked. Most of the CO2 that we produce is for energy, burning fossil fuels for electricity and transport. So, without getting too political, we can turn off lights and appliances, we can drive less, we can buy less, we can recycle, we can use less water, and do all the things that we know are good for the planet. We can and should keep doing those things. But there's one thing in particular that I want you guys to do, and that's leave here today with a message. The concentration of CO2 in the atmosphere is at an all-time high and is increasing. But carbon dioxide isn't the problem. Plants need carbon dioxide to survive. It makes soft drinks fizzy. It's used quite literally to put out fires. The problem is not carbon dioxide, but where it is and how much of it there is. Take another example, soot. It's the fine black powder found in smoke when something burns without enough air. It too has a greenhouse effect when in the atmosphere, but another name for soot is carbon black. When used in a battery, carbon black improves conductivity and increases efficiency. Soot/carbon black is mostly carbon, the same element that's in carbon dioxide, the same thing that fills a graphite pencil, and the same thing that makes diamonds. So the message I want you guys to leave with is that there are 430 parts per million of CO2 in the atmosphere, but also there are carbon solutions to carbon problems. And that's all I've got. I'm going to be chilling underneath the earth if you guys have any questions or want to hear the photoacoustic effect.